So Sentinel is Sentinel data are distributed through the Scientific Data Hub. So the only thing you have to do to get this data is to register. It's a free registration. This opens you a free web page from which you can query the database, all the archive of Sentinel data, make your selection, and download the data. Nice, very, very nice, very powerful. We thought this is nice to be added also this feature to SARscape. So basically in 5.2 you have in the SARscape menu, in the import area, you have also the Sentinel download functionality. So basically you have access to the same interface through a IDL, so through a ENVI module. If you click on this, you will get this panel. So basically you can select from within ENVI Sentinel data in your area of interest, or even if you have already some reference files, some file you already downloaded, you can provide a list of files and ask to this tool, please select in the InSAR archive all the Sentinel data that are part of the same area, that cover the same area with the characteristics I'm going to tell you. You can specify reference SAR files, but you can also specify your region of interest through a shape file you can enter in this dialog. So you can provide a polygon or several polygons saying, yes, I am interested at this geographic region. Of course, you're allowed to provide your username and password. This is going to register you inside the Sentinel Scientific Hub, and you can specify also in coordinates your region of interest, your period of interest, start and stop, day, month, and year for the selection, and all the options about I want a descending, ascending, all what you can use to refine your search. Then you will provide a progress file name. This file will contain all the information about the files that has been found, that has been downloaded. And so if you are going to repeat this query in some time and provide the same progress file name, basically the module will check, will identify the files that have been already downloaded, and so will work in an incremental way, updating the results of your search and downloading only the new files of interest for your project, for your application. So this is allowing you to work also in an incremental way to continue to monitor a certain area and download only the new files acquired regularly, as said by Sentinel, on the same area. So the outcome, the results of these is sometime after, of course, Sentinel files are quite large, from several hundreds of megabytes for a ground range product up to 6-8 gigabytes for one SLC product. So depending on your connection, you have to wait a few minutes, and the result will be one zip file containing each product. So you will have a series of zip files, one for each of the products you requested and the outcomes of your query. So if we are going to unzip this file, of course you will obtain a corresponding directory, and this directory with the same name of the product will contain a directory tree. So a Sentinel product is quite a complex product containing some preview information, some annotation, measurements, so the real data, and so on. So you don't have to be scared of these. The main information we are going to use of these is what is called the manifest safe file. So is a single file that is containing all the information about what is stored in this product. So if we switch back to SARscape, we will then use an import function to convert from the Sentinel format into the standard SARscape general format. We will include the manifest file in our input file list, and we will have the option to also provide orbit information. Sentinel has a precise orbit measurement, so the products come already with quite good orbital information. Quite means good enough, of course, for amplitude applications, for precise geolocation based on no ground control points. So the orbits are very fine already for amplitude informations. For interferometry, it's important to refine your orbits. You can download orbits from a website located at ESA. Unfortunately, the download is not automatic yet, but you have to manually select the orbit files that are important for you, and you can either include the orbit information here for each of the files you downloaded, or you can put the orbit files. Orbit files cover several frames, not just one frame, so you can create a local repository for your orbit files, tell to SARscape where this repository is located. So if you go to the SARscape preferences, you can see the Sentinel-1 orbit directory. So if you indicate the location in your system, local or in your intranet, the directory where these orbit files are located, well, the import function of SARscape for Sentinel data will search in this directory for the orbit that corresponds to your files to be imported, and will automatically merge the orbit files with your products. And this is very interesting, very important for the interferometric processing. At this point, you will be able to select your manifest safe, and in this case we have just one single data set to import, but of course if you have several products resulting from your download, you will be able to import several products at once, providing all the input files in this input file list. Then we can switch to the parameters tab of the Import Sentinel module and select and activate the rename the file using the parameters flag. So in this case, we will ask SARscape to extract the important information about your product. That means acquisition, start and stop time, descending or ascending orbit, polarization, and use this information to create automatically the name of the output imported file. In this case, the standard name is well, the same of the input, because SARscape does not know this information before the import already, but at the output, if we activate this flag, the files will be renamed automatically according to the information found in the product. So we will start the processing, and basically this is the result of the import of the file I selected and I showed you. In this case, we have a Sentinel-1 acquisition over Japan. This is the south of the Kyushu Island. We see sea here in this area, and we see three stripes, three vertical segments. So basically, these are Sentinel-1 interferometric wide swath data acquired in what is called the TOPSAR mode. TOPSAR is a SCANSAR-like mode. That means that the antenna is steered, the pointing of the antenna is changed after a few lines from near range to mid range to far range to acquire different sub-swaths. So we have to think that we are looking from left to right. The satellite is flying somehow from the bottom to the top of our screen, and the first swath, sub-swath is acquired, then the second, then the third, and so on. So one after the other in a cyclical process. This is a SCANSAR-like, but during the acquisition, the antenna is also rotated, electronically pointed along azimuth direction, is steered to minimize the effect of scalloping. So we have a very continuous acquisition, no bending, no change, no variation of the quality of the data along azimuth due to this TOPSAR acquisition mode, and very large swaths. So we are looking here at one image acquired with about 20 meters of resolution, so good resolution, but covering 250 times 200 kilometers, so it's a very large swath. You see here we have a name obtained automatically, generated automatically by SARscape during the import phase, and we have a VV image. Another nice feature of Sentinel is that at least so dual polarization data can be acquired at the same time. So in this case, the dual polarization data are in the VV, so vertical polarization, copolar acquisition, but we have also a cross-polar acquisition, so a VH acquisition. In this case, as expected, we see that the sea is very dark, water is very dark in cross-polar, in cross-polarized data. So we see that the little islands and the ships are popping up out of our black, very dark sea area. So this is a visual result, but actually this is what SARscape extracted from our data. I requested to download and to import the SLC data. So SLC are formed by several bursts, so few lines in one swath, followed by few lines in the next one, and so on in a cyclical process. During the import phase, SARscape is extracting all these splitted bursts in subdirectories. So basically we have a subdirectory for the VH and another subdirectory for the VV single bursts. So these directories are storing all the single files. But during the import, SARscape is generating two additional so pieces of information. The first one is a SLC list file. You can see it here. So this is basically an index file storing all the names, all the information of the single bursts belonging to the same acquisition. So is an index of all what is contained in these subdirectories, and is creating a mosaiced power file merging together all the single bursts so that we can visualize and use the amplitude information, treating it as a single file. So if even starting from complex data we are interested at amplitude applications, we can directly start from this power file, that is the mosaic of all the single bursts. If vice versa we are interested at interferometric applications, then we're interested at using the single bursts all together. So basically, if we see this is the content of our split bursts directory, a sequence of SLC1, SLC2, and so on. These are the complex data for all the single bursts. They have been mosaiced together in the power image to show the amplitude, but the interferometric processing will start from this elementary information. Of course, we will not have to handle all the single files one after the other. SARscape is going to use the SLC list. So basically, if we have a look at the interferometric workflow, for instance, one interferometric module, and I started here, for instance, the InSAR digital elevation model generation workflow, and if I select input file, I am allowed to provide a single look complex as well as a SLC list file as input. So basically, if I provide a SLC list file in input, all the single bursts will be used during the interferometric processing. So I will provide the input SLC list for my master, the equivalent SLC list for my slave, and SARscape will create all the single interferograms for the pairs of bursts, of corresponding bursts obtained from the master and from the slave, create the single interferograms, and merge together, mosaic together all the interferograms to form a global interferogram for all the bursts belonging to the same acquisition. So the input unit is a SLC list, but after the interferogram generation, we will go back to the image, so a single image representing the full composed interferogram for the whole area. So It has been a big work to support Sentinel data, so we added a lot of functionalities to SARscape 5.2. As we saw here, important, I think the goal is to help to simplify the life of the user a lot. So a download function, so you can run this function continuously to download your free data from Sentinel. Then indeed, we support precise orbits in two formats, restituted and precise, and you have to know that the accuracy of the restituted orbits in this case is already very, very good, so you don't really need to wait for precise orbits that come about 20-24 days after the acquisition of the data. So you need several days to get the precise orbits, but already the restituted are very, very, very good, much better than one contained in the products as soon as they are generated. And indeed, we updated the sample selection and the slant range mosaic tools to treat bursty data. So if you have two frames of Sentinel-1 data, one after the other, then you can mosaic them together to form a joint group of, if you want to create a new SLC list file, joining all the bursts of the two frames. Vice versa, if out of a very large frame you are interested to look only at a portion of your scene, so extract a few bursts covering your area of interest, the sample selection tool can handle SLC list files in input. Indeed, you can be interested at amplitude processing of Sentinel data. Already many functionalities were included in 5.1. Now you have a full support for stripmap, interferometric wide swath, and extended wide data in the amplitude workflows of SARscape, as well as in the step-by-step tools. So you can use all the amplitude-based tools with ground range data, but also with the data detected out of the complex data for amplitude processing. Indeed, what is new is a full support for interferometry with Sentinel data. Stripmap, very similar to what was included in SARscape up to now, but full support now also for TOPSAR for interferometric wide data for Sentinel-1. This means that you need in particular to handle the bursty mode, so that means merge together several interferograms. This is quite simple. What is very important is to avoid discontinuities between those bursts, and this calls for a significant update in the co-registration module. This means that you need an accuracy in the co-registration in the order of 1/1000th of a pixel, so very, very accurate co-registration. To reach this, we added a spectral diversity tool in the co-registration, so you can obtain a seamless combination of the bursts of the interferograms obtained from different bursts, thanks to the fact that the co-registration, in particular in azimuth, is now much more precise, so very much accurate. This engine to support the interferometric processing of Sentinel data flows into all the interferometric processing modules. This means workflows for DM generation, displacement maps generation, coherent change detection, both in the workflows and in the step-by-step processing. But very interesting, this engine allows you to perform so interferometric stacking processing of several Sentinel-1 acquisitions to perform persistent scattering processing and or small baseline S-bus processing. So all the interferometric modules have been updated to handle interferometric processing of TOPSAR data. Indeed, to handle this data, we added a new group of preferences. If you go to SARscape and you are going to process TOPSAR data obtained from Sentinel, you go to your preferences, load preference, and you will see a new set of defaults. Selecting these Sentinel TOPSAR defaults, all the tools of SARscape will be configured properly to support at best the processing of Sentinel-1 complex data. Okay, before starting to show you some results, I show still some issues with the Sentinel data. These are Sentinel data obtained from ESA, no SARscape processing. And if we look at SLC data, but also if we look at ground range detected data, this is a pair of images obtained from the same raw data, from the same acquisition over the Amazon forest. So we expect very continuous acquisitions, distributed target, very homogeneous. And we see, nevertheless, at the merge of the different sub-swaths, we see some discontinuity. We see them, but these are below the requirements, so is I think 0,1, 0,2 dB of radiometry. So negligible from the requirements point of view, negligible from many applications, still noticeable. So ESA is well aware of this effect. They are working to minimize this effect, but at the present time, this is still according to the specification. So no problem for the application, but still we will see in many of the examples we are going to see today this effect, so of residual missing calibration contained inside the data as they come from ESA. First example, let's look at amplitude first of all. In this case, we have a set of 3 acquisitions, 3 Sentinel-1 acquisitions obtained over Greece and Turkey. So it's a large, we are starting to be used with these large data. It's large acquisition from Greece, 250 kilometers east, we reach Turkey, and this data set has been acquired this spring, so from February to March, April, in a period where there have been severe floods events in this region. So we start to see many areas that show up in purple, in blue, they correspond to areas flooded in different days in the same flood period. As I said, Sentinel, very nice, large areas, but also still an appreciable and acceptable resolution, 20 meters. So if we zoom in, for instance, in this region, we see at full resolution this little river, and we see these blue areas that correspond to areas flooded just after the end of February of this year. If we move a bit toward east, another region, we see more purple colors, so we see areas flooded some few days after these. Over Europe, we have a continuous systematic acquisition scheme. Every 12 days, you have a Sentinel data, so very, very nice for monitoring, very nice for continuous coverage of the whole of Europe. Then we move even more eastward to Turkey. In this area, there are a lot of rice fields, but it's not. These floods are not related with the flood period of the rice fields. It's just view of these generalized flood events, and so we see different colors related with a different timing, different day of the flood of different region. So early floods in red, blue floods, and so on. So in a single frame, in a single swath, we can cover very large regions. So we don't need to process thousands of images to obtain a very large coverage of areas with Sentinel. Just to give you an example, this is a mosaic we created using data from Sentinel-1 acquired just in one 12 days cycle over Southeast Asia. So it's quite impressive for me. Mosaic in 12 days, of course not only here, but in this region, already in 12 days we have a full coverage. We are just missing this single frame over India, unfortunately, to have a not complete mosaic, but we see that in 12 days we have a very consistent mosaic, very consistent coverage. So we are spanning from Philippines to India, and just because we limited the mosaic to this area, and we see that we have a almost seamless mosaic, so we don't see discontinuities. We see only here discontinuity because this track was acquired at the end of the 12 days cycle, and this track was acquired at the beginning. So already some changes in the phenomenology on the ground, but just applying a simple mosaic using only nominal data, we have this very well calibrated mosaic, and we see we see colors. We see some yellow, some bluish colors. So this is an indication that in this case, we don't have only a Sentinel wide swath coverage in one polarization, but we have both polarizations available. So we have double the information for each pixel on this very large area. And we can indeed zoom in, so we see the type of mosaics at country level obtained in one 12 days cycle over India, over Myanmar, over Thailand, Vietnam, Laos, Cambodia, Philippines, and Java. And indeed, if we zoom in, for instance, here we are in the Mekong River Delta area, we see the type of resolution we obtain. Very nice resolution. Indeed, in this case, we applied speckle filtering, mosaicing, geocoding, all the proper processing to obtain this type of mosaic. And again, these are dual polarized data, so we can see already the contribution from the thematic point of view of the two acquisitions, the two polarizations acquired at the same time. And again, I want to highlight that all the processing has been done in an automatic way without the need of a ground control point selection, so everything is properly geolocated and calibrated with the nominal parameters and with the proper software. Okay, nice. What about the phase? In this case, we see an interferogram still in slant range geometry of one interferometric wide swath, so that means of one TOPSAR acquisition obtained from Sentinel-1. We see 1, 2, 3 subswaths. We start to be used to subswaths with Sentinel, and we see nice colors everywhere. This is a 12 days interval acquisition over Syria, so very good coherence. We have almost everywhere high coherence. 12 days is a nice interval, short interval to have to try to reduce the amount of temporal decorrelation. We see the swath, but we see the swath more from the brightness of our image. Please remember that, please consider that this is a full color composite where the color comes from the phase ranging from yellow to light blue to cyan, while the backscatter is modulating the intensity of our image. So if we have a little discontinuity of the backscatter at the edges of the subswaths, as we know from my previous slide, well, we are going to see it even if in these color-coded representation, not because we have a jump in the phase, but just because we have a discontinuity in the backscatter. So here we see that we have very continuous interferogram, so these from the interferometric processing point of view of TOPSAR data means that the co-registration is very accurate, again 1,000th of a pixel, and the only no problems, but the only noticeable effects come from the backscatter. Of course, what we see are big phase patterns. In this case, we are not speaking of topography. This is a flattening interferogram. We are not speaking of displacement. This is not a earthquake area or huge subsidence. No, these are mainly atmospheric artifacts. So even in 12 days, we can expect that our atmosphere has a significant variation, significant heterogeneity from one date to the next one. So we see these even more if we enlarge our area of interest. So if we look at these very large areas, we notice more and more those atmospheric artifacts, these unwanted variations. So if we are interested at local effects, very big from the wavelength point of view effects, we can still consider single interferograms. But if we are interested at very precise effects over large areas, well then the importance of interferometric stacking techniques, so small baseline, PS approaches, are even more important for Sentinel to minimize, to reduce the impact of those spatial and temporal variation of the parameters of the atmosphere through which our radar signal is propagating in the different acquisition dates. Let's move from Syria to Japan. Here we see a full frame over the area of Tokyo in the center. We see the Fujiyama volcano on the west of the city. We see some discontinuity in the radiometry, again, known. And what if we switch to phase? Nice, we see that, we see nice colors, we see some residual baseline effects, but we see good co-registration, no discontinuity in the phase anywhere in the interferogram. We see areas where we see good coherence, nice colors, and we see low coherence over the vegetated areas, volcano, forest here in the northwest part, Accone volcano, low vegetation, so a lot of vegetation, low coherence, but we see nice performances of the interferogram generation of this area. And this is the corresponding coherence map. We see no discontinuity, the coherence is continuous through the subswaths. We see good coherence in white over the inhabited areas, lower coherence as expected, because we are speaking of C-band data over the densely vegetated area. Even with 12 days, we cannot forget the temporal decorrelation over forested areas. And this is a false color composite of our complex coherence and our radar backscatter, again, where the green areas correspond to the vegetated areas, low coherence, good backscatter, red and yellow areas, high coherence, strong backscatter, urban areas. Nice, let's move toward the south, toward west, to Kyushu, and let's have a look at the Sakurajima volcano. So the Sakurajima volcano is one of the most active volcanoes in Japan. It's an explosive volcano, so it could be very dangerous. And in this area, there are also atomic plants located. So it's a dangerous area. It's nice to have the opportunity to monitor the area with Sentinel, for example, but of course with PULSAR-2. It's an area where SAR satellite can play a very, very important role, in particular for not just the mapping of some event, but for the monitoring, continuous monitoring of the activity. So for instance, here we can see some interferograms Sentinel is acquiring every 24 days in ascending and 24 days in interlaced in descending. So Japan is very well covered also by the Sentinel-1 mission and of course by the PULSAR-2 as well. And we see here interferometric phase, the top of the volcano, some effects of atmosphere. Again, the volcano is quite stable in one cycle. In few cycles we start to see something, but indeed we can think, looking at this phase, that relates with the topography. Here we have effects of correlation between the topography and our atmospheric artifacts. But we see here in this acquisition, we see a lot of fringes. So basically, in the month of August, around August 19th, there has been a severe inflation, strong inflation, and the start of a strong eruption of the Sakurajima. So we still see big deformation. And if we combine 15 images in a stack or in this area, we can look at this event at full resolution, and we can generate, with a small baseline approach, a cumulative average displacement rate map of the whole area, where we see the strong displacement that is affecting the volcano caldera. So there is an inflation of the volcano that creates an uplift and east-west deformation. If we go to more severe events, we can move to Chile. So in September 16th, there has been a very severe magnitude 8.3 earthquake in Chile. It's a very strong earthquake. So the deformation affected a very large area. So we have to combine several frames of Sentinel together to have a full coverage of the event. Here we can see that if we merge together 5 Sentinel frames, we reach a stripe length of about 1,200 kilometers, so it's a very long stripe. We can process it interferometrically all together, and honestly the processing time was much less than what I expected, so it's about 1 hour or a bit less to process one single frame. So in less than 5 hours we had a full 1,000 by 250 kilometers interferogram, covering the whole of the deformation pattern. So you can see many fringes. Each of them corresponds to 2.8 centimeters of deformation, so a few meters of deformation altogether. So at this point we still see effects, local residual effects due to atmospheric artifacts. We can imagine that well, these few centimeters of atmospheric artifacts are really not important compared to the several meters of displacement measured in the area close to the epicenter of the earthquake. So what we did here was to mosaic together several frames and process them in one piece to optimize the co-registration, to have no discontinuities through the whole area, and to cover the full area impacted by the deformation. 20 meters resolution, we have also, even if it is not the proprietary acquisition mode of ENVISAT, you still have the strip map mode, supported indeed by SARscape 5.2. So we go to Napa Valley, California, struck by an earthquake, magnitude 6, fortunately a bit less powerful than the one in Chile, more than 1 year ago. We had also acquisitions in stripmap before and after the earthquake. This is an amplitude image on the area. Coherence image, very good coherence in 2 cycles of Sentinel-1. And this is the corresponding interferogram. So we can see at high resolution, about 3 meters resolution, the full pattern of the deformation. As said, well, 12 days of repeat cycle. So if we have interest at exploiting interferometric coherence from a thematic point of view, it's nice to see that 12 days and very controlled orbital tube allow us to have very stable coherence conditions in non-vegetated areas. Here is a color composite mosaic of Sentinel coherence maps. So here we have 3 coherence maps. That means 4 acquisitions, and we formed 3 pairs, one after the other in the time. We see here on the bottom left of this image the city of Turin in Italy. Fiat is established somewhere here, and we see that the city shows up in white in this color combination. This means that the coherence is always very good, is very stable, same value, very high value in this color combination, as we hope. And we see colors showing up in cultivated areas. Here is a rice growing area in Italy. You have also vineyards here in the north, and of course we see colors related with the changes in the vegetation, but we can distinguish them very well from the stable areas, showing always the same interferometric high coherence. If we go on in the period, so 3 cycles after, we still enter, and we enter spring, we still see the city very stable interferometrically, coherently, and we still see the evolution of the agriculture. So the controlled conditions of the acquisition of the Sentinel data help us a lot in the interferometric processing, but also from the thematic point of view, even if we are interested at coherence and exploiting the coherence from for thematic applications. or exploiting coherence for complex, so for coherent change detection, together with amplitude changes, covering very large areas. Here we are at the border between Syria and Iraq, and in this case we have a full Sentinel-1 frame, interferometric wide swath, covering a large area. Dry area, so we see big amount of red. Red in this false color combination is indicative of high coherence. And if we zoom in at full resolution, already from the amplitude we start to see some interesting effect. Here we have an acquisition in October, so a village here, another area with some little urban areas here, little villages, and bare soil here in October. Then in March, April, and the mid of April, we see here linear features appearing, and we can think pipelines, different objects could be indicative of the, so interpreted for this high backscatter. Interesting and curious for me is that these bright lines don't have always the same shape. So these straight lines become banded here, so they cover more or less the same area, but they are moved, shift from one acquisition to the next one. And if we generate a false color composite of these two images using also interferometric coherence, we see that, of course, the coherence is very high here, dry conditions, but we see big changes of the backscatter, low coherence. Here, these lines are kind of duplicated lines. This line is the first acquisition, the second acquisition, the same shifted line. So these are objects that are providing a very strong backscatter in VV in copolar acquisitions, but they are shifted from one date to the other. We can introduce in this analysis also the second polarized image. We can use a VH acquisition. So here I have a VH acquisition in March and a VV acquisition in the same date. So what happens? I see that the bare soil is of course providing no backscatter in VH polarization, but my objects are still reflecting a lot. So this is an indication of depolarizing objects, very random objects providing a strong backscatter, but not a kind of double bounce. So it's not a very well-organized reflector that we are looking at, but is a kind of random object, random from the polarimetric point of view, but still providing strong backscatter. So we can move to other areas and see that there are similar effects. October, no lines. March, April, those lines are still very visible, but they are moved, they are shifted over the time. And of course, the same effect, big variations both from the coherent and from the backscatter point of view. In the polarization dimension, we still see these objects, strong reflectors, random from the polarimetric point of view. Last area, third area, we move here and we see that here we have a combination of effects. We have again linear features, but some of them are always constant in their position, and some of them are evolving with the time. The backscatter tells us those lines are changing, are not coherent and varying the backscatter. This line is constant from the backscatter point of view and always showing high coherence, high stability of our phase information. So in this case, in this area, we can distinguish two types of objects. One, strong reflection but changing a lot, and one not changing neither from the backscatter nor from the position nor from the phase point of view. What happens in the polarimetric dimension? Well, some objects are still visible here, random objects from the polarimetric point of view, and this object, this linear feature disappeared. For me, this linear feature is some kind of pipe of stable construction that is always there, showing a nice stable double bounce effect. So from the polarimetric point of view is strong reflecting in the VV polarization and disappearing in the cross-polar VH acquisition, while the other object is showing up again in both polarization. Which type of objects am I speaking about? I don't know exactly, I was not there, but my impression is that we are looking at an area that is very unstable from the political point of view, from the and we are probably looking at effects like fences, like metallic objects strongly reflecting, but not well organized, not geometrically stable from the polarimetric point of view, so providing a random polarization in the backscattered signal. So some type of fences, metallic fences, could be a good explanation, and those fences are shifted, are moved from one acquisition to the next one to block areas or to surround areas, but they are not permanent with the time. So we can use Sentinel data to monitor and to provide change detection information over very large areas at high resolution. Nice. But I hope you can say the same, but Sentinel is not, so SARscape 2 is not only Sentinel-1. Indeed, the Sentinel is a nice object, but, well, PULSAR 2 is as nice as Sentinel indeed. So what did we do for PULSAR 2? Well, we already had consistent support of stripmap data for PULSAR 2 in SARscape 5.1. Sorry. What we added is SCANSAR interferometry for ALOS-2. Unfortunately, we had only a limited number, so 2 acquisitions available to us to test the software. So it's what we call still in a preliminary support phase. We are continuing now the test after the release. We got, fortunately, thanks to our Japanese colleagues, more data to test the package, but we released already a nicely SCANSAR interferometry package updated to allow you to provide, to generate interferograms for ALOS-2 SCANSAR data. In particular, if you are interested at this feature, you should use data processed in full aperture mode, not in burst mode. But with full aperture data, you can generate from SCANSAR acquisitions of PULSAR 2 very nice interferograms. We included the support of SAR data, airborne data from DLR, and we added some polarimetric features to support this data test, and we also started to enter into marine applications. Not yet ship detections, but we started to add support of AIS transponder data. So if you have data acquired over marine area, over sea or ocean areas where there are ships with transponders transmitting their position regularly over the time, you can import those data, convert them into shapefile, and incorporate them together with your SAR data. Okay, here an example of SCANSAR interferometry based on ALOS-PULSAR 2 data. Another earthquake, unfortunately. The area of Kathmandu in Nepal was struck by a severe 7.8 magnitude earthquake in April of this year, and we see a amplitude image over the area, and we see the deformation pattern obtained from a full frame of PULSAR 2 data over the area. So we see that also in this case is unfortunately very nice to have access to large area data. With one acquisition, we can consistently cover the full pattern of the deformation for several hundreds of kilometers, covering all the region of the valley around Kathmandu. And you see also in this case we have 5 sub-swaths covering 1, 2, 3, 4, 5, covering the whole area. So they have been processed and merged together in a seamless way. So no phase discontinuities in this large area interferogram. Interferometry is also in this case interesting both from a quantitative and from a qualitative point of view, looking at thematic applications over Thailand. Here we have a false color composite imaging including both amplitude variations and complex changes derived from complex processing of SCANSAR data in the dry season and in the wet season in the agricultural, when the agricultural period started. So here we can see queries maps that help us to monitor, to follow all the evolution of the agriculture in this region. So again, have access to large area data, SLC data, allows us not only to look at all the interesting interferometric applications, but also at very interesting thematic applications relating with agriculture, with forestry, where the coherence can play a very important role. Airborne data, in this case, of course, we switch from, say, high resolution to very high resolution. Here we have SAR data. SAR data comes from DLR. And here we have a L-band acquisition, full polarimetric acquisition, 1 meter resolution obtained over an area in Germany. And we see a classical Pauli decomposition from the polarimetric toolbox in SARscape. SAR data, again, 1 meter resolution, very interesting. And you see vegetation showing up in green in the Pauli decomposition, the third component of the decomposition. And if we switch to the Krogager decomposition, we see, okay, the vegetated areas show in a different way, but what is very nice, we have the capability of distinguishing those man-made features, very regular, very flat surfaces. We can imagine this is a solar panel plant in Germany, so for the production of electricity from the sun, that has been, so these type of features has been nicely identified and selected by, highlighted by the Krogager decomposition. So we added the Krogager decomposition in the InSAR module of SARscape, thanks also with the collaboration of, with Dr. Krogager himself. And here, another example, again, entering a different type of applications, not land applications we are used to look at with SARscape. We are starting to include something in particular specific for marine applications. Here we see a Sentinel-1 data set over Greenland covering a large area, and in another large area we have a lot of ships. So if we obtain for the same time of acquisitions, for a period around the acquisition of Sentinel-1 data, transponder data from X-axis Earth, I think in this case, we have the location of ships who are transmitting with their transponder, and we have the path of these ships, the route of these ships. So basically this is a shapefile that has been generated by SARscape, importing the AIS data, converting them into shapefile, and allowing you to overlay the location of the ships with your radar data in background. So the next step will be to identify, to detect the ships from the SAR image and try to merge the SAR-derived data with the AIS data to confirm the identification of the ships, to see which ships we did not find with the ship detection tool, and to identify which are the ships that were detected but were not transmitting with their transponder. Okay, now just as a kind of summary of what we did, the big work we did, in particular a lot of updates here and there of the code, but many in the interferometric part. We updated both the PS and the S-bus modules significantly. The PS has been updated to cover large areas, so we have a new algorithm to merge the different quadrants, the different quarters in which we divide the interferometric stack during the PS processing. Now you have a very, very continuous coverage. No discontinuities shall be expected even if you cover large areas. we created a bridge between the geophysical modeling and the SBAS module. So basically you can also process with SBAS time series across significant events like earthquakes, where your time series have significant discontinuities. You can include the outputs of the geophysical modeling to remove the effect of the earthquakes and look at what is happening before and after in the time series. As I said, we updated the sample selection and the mosaicing tools to support bursty data, SCANSAR data, TOPSAR data, so you can both subset your SCANSAR and TOPSAR data, SLC data, or mosaic them to cover small or very big areas. Then we updated our multi-aperture interferometry and amplitude tracking chains. But very important was a very deep update of the co-registration and interferogram generation module to support TOPSAR acquisitions, spectral diversity co-registration, very precise, and all the module has been significantly rewritten, so we improved a lot in terms of robustness, accuracy, but also in terms of computational performances. So there has been a significant speed up of the module. Last but not least, nice features have been updated in SBAS, incremental SBAS, so you can process a first set of data, Sentinel in the last, I don't know, 6 months. Then in 2 days you are going to get a new Sentinel acquisition. You don't have to start from scratch again, but you can just add the new Sentinel data and perform incremental update of your SBAS processing. And we also updated the capabilities of SBAS to handle disconnected time series. If you have losses of coherence, no connections, you can still create derive a linear time series of your data, even if you have disconnected time series. As said, significant speed up. Just to give you an idea, let's take an example one, Cosmos SkyMed full frame, about 1 gigabyte per image. So the original time was more than 1 hour to process a full frame at full resolution. More than half an hour was due to the co-registration, so to the synthetic interferogram generation, in particular important if you use the digital elevation model during the co-registration. We updated these to handle in a different way the memory using OpenCL to perform parallel processing, and from more than half an hour we went down to a little bit more than 6 minutes, so a speed up factor more than 5. Co-registration was already exploiting optimized Fourier transform kernels from Intel MKL, 3 minutes, but including also parallelization of the fine co-registration, fine estimation, we parallelized it to go to 2 minutes. Resampling was not parallel, so introducing a TBB parallelization of the code, we went from 26 minutes down to 50 minutes. So altogether, from more than 1 hour, a factor more than 2 of speed up, we went to less, so to less than half an hour, 26 minutes. So at this point you can see a significant improvement, a factor 2, but still with a good part of the code in CPU-only TBB implementation in parallel, but not yet OpenCL. So the next step will be still to decrease a few minutes of processing, exploiting OpenCL also for the remaining steps, parallelized but not yet exploiting GPU. Still, I think with SARscape 5.2, you can exploit as default, as it is set, DEM-based co-registration to obtain a very precise co-registration in an affordable amount of time. So I hope this was in this way was possible to show you that we added a lot of functionalities to SARscape 5.2 to do what? Well, to improve the capability you have in your hands with SARscape to perform operational processing, exploiting Sentinel data at large scale. You can see here a mosaic obtained over the whole country of Hungary with Sentinel data. You can process very large data sets. You can process PulsarTwo data very accurately. Here is the island of Sakurajima and all the region of southern Kyushu. So very operational applications you can perform exploiting SAR data and SARscape 5.2. Thanks a lot.